Okay, number 3. Here we're talking about something called a removable discontinuity. And that is the math speak, the vocabulary word that we use in math whenever we're talking about a hole that happens to happen in a graph. Okay, so these are sometimes called holes, but formally they're referred to as removable discontinuities. Okay, and you find a removable discontinuity when this happens, when you can reduce a rational function by factoring and canceling. So the only time you can cancel is if you have parentheses on top and parentheses on bottom. So you only cancel with multiplication. So when this can occur, the graph of the rational function has a hole where the vertical asymptote would have been. Okay, so we find the vertical asymptote, but then something funny occurs and you notice that there's going to be a hole. Okay, so you can also tell that the graph will have a hole when you have an x-intercept and a vertical asymptote at the same place. Okay, so since we haven't talked about finding x-intercepts yet, or maybe you have, then you'll know what this means. So here's one example that I'm going to use to find the asymptotes and holes of the rational function. So from before, we find the vertical asymptotes by setting your denominator equal to 0. So let's do that. 9x squared minus 9 equals 0. So x squared equals 9. So square rooting, we have x equals positive and negative 3. Okay, so we would have a vertical asymptote at positive and negative 3, but this also happens. I don't know why I wrote if, but anyway, we can factor this new denominator here. Okay, right? X squared minus 9 is a factorable quadratic. So we end up with x plus 3 over x plus 3 times x minus 3. And because we have the exact same thing on top, x plus 3, as you do on the bottom, we can cancel that out. And the graph of f will look exactly like this graph. 1 over x minus 3. Okay, so this is where we're going to find your asymptote, and this is where we're going to find the hole. The thing that cancels out is where we're going to have the hole. So we're going to have a hole at x equals negative 3. We're going to have an asymptote at x equals 3. Okay, we'll talk more about this later, what it means graphically, but for now, just know that the hole occurs at negative 3 and the asymptote occurs at positive 3. So let's do the same thing for this one. So on top, I have 2x squared minus 2, which we should know has a 2 in common, so we'll factor out the 2. And then the top can factor 2, x minus 1, and x plus 1. Okay, so there's your numerator completely factored because we need to see if we can cancel anything out. So the bottom factors to x plus 5 and x minus 1. Those are the numbers that multiply to give you negative 5, but add to give positive 4. So x plus 5 and x minus 1. So you notice that the x minus 1 on top can cancel with the x minus 1 on the bottom, which means here we're going to have your asymptote at x equals negative 5. And here we're going to have your hole at x equals positive 1. So when the graph approaches that x value of 1, we're going to have a hole in the graph, but we're going to have an asymptote at x equals negative 5. Okay, so let me show you real quick what that actually looks like. This won't be perfect, of course. So we have a vertical asymptote at negative 5. And the graph is going to do something, something like this. But over here, when it gets to positive 1, it's going to have a hole, and it's going to continue on. So this one has a vertical or a horizontal asymptote at 2. So we'll talk about graphing them later. But right now, this is what the graph will look like. So at x equals 0, it has a hole in the graph. And at x equals negative 5, there is an asymptote. So that's the difference between an asymptote and a whole. Okay, fantastic. That is all.